Just to verify, how's your name pronounced?
It's usually pronounced Ange. It's commonly mispronounced, but it's so commonly mispronounced that I don't mind. Like any kind of pronunciation is fine, but I think that's the standard pronunciation.
Again, I first learned about you through my co-founder Nico. We're both big fans of graphics and real-time simulations, and obviously audio technology. We first saw your early work, just first principles making engine simulations. Could you first maybe just for us and just for everyone who's going to be watching, talk a little bit about your background and how you got started?
Sure, yeah. Um, originally my background doesn't really have anything to do with what I do now, so it's not really relevant. I worked in investment banking for a while. That was mainly in like derivative pricing and stuff. And then after that, I worked at Amazon. I worked in Amazon Alexa. And then I worked at Google for a bit. And that was around the time when I created Engine Simulator. And yeah, so my background in the tech industry is pretty standard. It doesn't really have anything to do with sound synthesis. The way that I got into sound synthesis is a little bit strange. So basically, I started working on a project car. I think it was, I don't know, it was a few years ago, and it ended up like costing a lot of money. So I wanted to figure out a way of taking all of the knowledge that I gained in that and actually turning it into something that was useful for my career. And this was the closest way that I could think to do it. And yeah, I don't know. I wasn't really expecting anything to come out of it, and it was a lot more successful on YouTube than I was expecting. And now I guess it's my job, and that's how we got here.
I feel like I guess that's my job now. Definitely describes a lot of my life too. So I understand that.
Yeah,
I also, yeah, come from a background really different than what I do now as well. So I totally, totally get that. I'm curious, what do you think is it that draws people to seeing you kind of build these simulations, and what do you think makes it exciting to people?
I think that there is. I think there's a lot of elements to it because I've always been interested in simulations, and I always found that the simulations that you typically get in video games are, I don't know, there's something missing about them. And I'm not really sure how to explain it exactly. Like, there's obviously something there, and a lot of them do have some utility, but I don't, it doesn't feel right for some reason. Like, you can kind of tell, like in a game, if you're interacting with, let's say, an engine or some kind of machine, you can tell that the approximation is very simplistic. And I always wanted a bit more than that. And I think that a lot of people have a very similar experience. And that is especially relevant in car games. This is probably the one genre where the audio design has not evolved that much in a very long time. I mean, the graphics have come a long way. The physics are really advanced now, but the audio is still it's advanced a little bit, but at a much slower pace than everything else. And it just so happens that that is a critical component of the car driving experience for most people. As you know, childish as that sounds, people like the sound of engines, and if that's missing in the game, that's like a important feature of the vehicle that's not there anymore. So by adding that and making it feel like, you know, it's like a real engine that responds like you're used to in real life, I think that that excites people about the possibility of potentially having that in racing video games. Um, and I think that's probably like the main element of it, at least in the context of engine simulations.
Yeah, I've always wondered about that too. Are you familiar with the old game Trespasser from the late 90s?
I don't think I've heard of that one.
So it was a Jurassic Park game. But it was made by this guy named Seamus Blackley, who later created the Xbox. And Nico and I've talked to him before. He actually has a PhD in physics, and he got hired to make this game. And it was because he was like this physicist is my understanding, I'd like to ask him. It was like one of the first games to have a full physics engine before like even like Half-Life 2. And not only did it have like a physics engine, for like, Newtonian dynamics, but it also had a like some sort of physics-based sound engine, which, because I think he probably assumed, well, of course, like if I'm going to do a physics-based engine for dynamics, I'll also do it for sound. And I don't know how sophisticated it was. But since then, I actually just, besides maybe 3D sound location and like applying like reverb effects and filtering, I just don't see very much physics-based sound engines still, at least that I've ever heard of. I see papers about it, but yeah, why do you think that is?
I mean, that's a good question. I don't know. I think that it feels kind of weird that I'm even answering this question because I don't have much of a background in like, I've never written a paper on sound generation.
Yeah.
The funny thing is that I got into it almost because I was so naive about the complexities about it. I just thought it would be cool to try, and then I tried it, and then I mean, I did spend a long time on it, so that's like part of it. But I didn't really know if it was possible or not. And most of the like in the tech, specifically the video game industry, most of the people that I talk to who are specifically in audio design, their main reaction was, I just wouldn't have thought this was possible. So, and it's kind of like it would just be like a fool's errand to even try. And that was kind of what I went into the project believing. Like I wasn't expecting the output to sound good. I just wanted to see like what could you even do with that kind of, just some like approximations, filling in the blanks where the processor is obviously not enough. What can you get out of it? And I don't know, it just ended up sounding better than I thought. I think that maybe there is a bit of a bias that, the people assume that the processor technology is not there yet to enable this. I'm not sure. I actually don't know exactly why that's the case.
Natalie is saying to show you this flag. It was a gift to us from another founder. Because we do this not because it's easy, but because we thought it would be easy.
Yeah. Yeah, exactly.
That's really fun. And that's what I love about your videos, by the way. You're just like, well, I don't know how to do this, but I looked it up and I guess here are the system of equations for like Euler's equations for compressible flow or whatever. You're like, I guess this is where you start. And you just naively start at first principles and just kind of work from there through mechanical systems and computational fluid dynamics, and that's just incredible to me. Which I love that you're just like, well, this seems to be the starting point. Let's see where it leads. And most people are like, in a sense, like have already told themselves from from learning from others maybe that this isn't how you would do it or that it's not possible, and therefore they never bothered to try.
Yeah, yeah. It's I think also I was in a bit of an advantageous position to undertake a project like this because obviously I was employed at the time and this was just something that I did for fun. So there was no real pressure on this working because and that's the other advantage of making YouTube content is that if something fails, that's still content. Like, you can turn a failure into a video. That's not really a problem. If anything, those like usually perform better. So yeah, it was kind of like I didn't really care if it worked or not, but I can imagine that if I worked at a game company, let's say they were making the next Forza or whatever, and I went to my manager and I said, "Okay, hear me out on this one. I'm gonna simulate the entire engine from scratch, and it's gonna make noise, and it's gonna be awesome." They're just gonna think that you're crazy because this is not like, and it kind of is crazy because the CPU requirements. I mean, it's doable, but it's not ideal. Like you're going to be using definitely an entire core, maybe two, which is probably too much for most video games. So it's almost like the idea is just a non-starter on paper. So I can understand why, like strategically, it wouldn't make any sense to undertake this project unless you were basically in my position where you have nothing to lose and it just so happened that you like making simulations. So I got kind of lucky on that, my positioning. Um, But yeah.
As I remember, so I mean, actually, my background originally was in physics and aerospace, and I was doing computational fluid dynamics when I was like, doing my master's. And that was right when CUDA first came out. And like CUDA now, anyone who's working in machine learning, everything we do requires CUDA, normally with libraries built on top of it. But the first use case that was really rapidly adopted for CUDA was CFD because it's so computationally intensive to do a large fluid simulation. Have you been doing anything on the GPU?
So up to this point, I actually have not used the GPU for anything simulation related. There are some issues as far as using the GPU for that purpose. Like a lot of it is latency related. I think that it might be possible. I just haven't really looked into it. As in, like, I haven't looked into it very much. A lot of the simulation technology that I've looked into is very much technology that hasn't been in the, what's the word I'm looking for? It's old. This is technology from decades ago that was used at that time, and it was considered to be like really computationally intensive in like the 90s or the 80s, even maybe back as early as the 70s. But you actually don't need much more than that to like get a primitive sound output. Like if you're doing maybe a 3D simulation, then the requirements grow quite quickly in that case, and then it becomes prohibitively expensive to do it on the CPU. But if you're just doing a one-dimensional CFD, and your segment size is, not extremely small, it actually works out to be basically right on the limit of what modern CPUs can handle. So I haven't at this point had the need to move to the GPU yet, but definitely like certain things could be sped up quite a lot on the GPU, but I'm not 100% sure. There are some other like complexities there.
So, in general, like, I mean, having done, fluid simulations, one of the hardest problems is they tend to be, they're a system of nonlinear differential equations. They tend to be very tricky from the like numeric stability perspective. What
Yeah.
sort of issues have you dealt with in terms of like numeric stability?
Yeah, I mean that is a problem because in my simulations, most of the literature that I'm following, they describe, and I've talked to like also some of the authors of those papers. They usually talk about simulations in the sense of, okay, I set up this simulation with, very specific parameters. I'm going to leave it to simulate a time slice of like, I don't know, a few seconds, a few minutes or whatever. They leave it run overnight, then they check the results like the next day or whatever. That's like a typical use case that I've seen for this kind of simulation. But the simulation that I'm working on doesn't work like that. It should be able to continue running for hours at a time without having any of these numerical instabilities just completely blow up the simulation. And this was a problem because the first time that I ran the simulation to generate audio, the more recent one that I've been working on, it just blew up instantly. So it's like, yeah, it really doesn't want to exist most of the time, but I found that like there are certain what's it called again? There are certain techniques that you can use that I think make it a little bit better. And these have also been known, like there are like flux limiters and stuff like that, which I use in the simulation. Some of them work better than others. A lot of it, actually, one of the craziest things that I learned about fluid simulations is there's a surprising amount of almost subjectivity that goes into them, which you wouldn't necessarily think would be the case. Like, and I thought I was crazy because I was reading through the literature and trying to understand, why is it that there are different flux limiters for like, wouldn't it just all be the same thing? But
Yeah.
apparently not. And the way that one CFD expert put it to me is he said, there are many ways to skin a cat. With his words, it's obviously like a kind of old-fashioned phrase now, but basically what he means is that there's just multiple ways of doing the same thing, which seems really weird to me because like wouldn't there just be one way to do it if it's supposed to be a scientific simulation? But yeah, apparently there is some degree of subjectivity and sort of like massaging that goes into making a successful fluid simulation. And in my case, I'm not necessarily bound by being scientifically rigorous. So I can, add certain approximations where I think is necessary. I can add certain code that will prevent the simulation from blowing up, even if it's not, completely scientifically sound. The exact scientific output of my software is not that important. So, yeah, it's like, I don't know, it's a lot of trial and error and using techniques that have been used for a long time to prevent instability like that, and also just making sure that the simulation is always running within the boundary that will mostly ensure that it's stable, but even then you're still not guaranteed. So yeah, it's complicated. I haven't even like fully solved that problem myself. My simulations still blow up sometimes, so I don't know.
Yeah, on the topic of like, yeah, there are many different versions of fluid dynamic equations that you can pick from. Like obviously, like you could kind of cheekily say like, oh, just start from Navier-Stokes, or just start from the Schrodinger
Yeah,
equation, work from there. In reality, anyone who's done it, like one, obviously there are just so many different forks in the road where you're just like, okay, do I care about energy conservation? Do I allow vorticity? Do I allow compressibility? How much? Do I allow things to change species? And like all of a sudden, there's like, thousands of different choices you can make, boundary conditions too, obviously. And so
yeah.
there's all different choices you make. And, so you have to then make all these calls. And yeah, it's like super subjective depending on what you want to do. And like from your perspective, like how have you been navigating that?
I mean, I think ultimately I'm sort of guided by, well, there are a few hard constraints that I have to deal with. Constraint number one, it has to sound good. So anything that destroys audio is just a non-starter. Like I'm the name is escaping me right now, but there are certain techniques that I tried for solving the Euler equations that just don't make good audio. Like it sounds really distorted to human ears. And there are other approaches that don't do that. So obviously, I chose the ones that sound the best. And the other restriction is it has to run in real time. So, those are the two hard constraints that I have to work around, and they have mostly dictated what I end up choosing. In the case of, like, for example, boundary conditions, they are probably the things that I've noticed affect the audio the most. So, if you use, like, let's say that you do like something really naive where you just, okay, I'm going to set the outer boundary cell to like whatever the conditions in the atmosphere are, which is the wrong way to do it technically. It doesn't make good audio, and it's immediately obvious, like the reflections that it causes, the spurious reflections and stuff, it just doesn't sound good. But then when I moved into a more advanced boundary condition that actually does take into consideration, all of the different patterns of flow that can be at that outlet, all of a sudden the audio sounds a lot better. So, it's a balancing act of choosing things that generate good audio, and also choosing things that work within the constraints of your average consumer CPU.
Yeah. So one thing that Nico and I both share a love of, Nico's my co-founder, they share a love of, and it was, I think one thing that we loved about your channel is we both love just like beautiful tools. Like there's another YouTube channel that Nico found where it's a game designer and he shows his memory management debugger. Like it's like a memory management tool he built for his C code. But it looks beautiful, right? It's like this
Mhm.
beautiful tool. One thing we just like love about your videos is like, you're not just focused on making real-time audio, but also visualizing it. And a lot of like, using different like particle effects and other choices for data visualization that looks amazing. And obviously it's for YouTube, but like you clearly care just as much about the visualization as the audio. Like what are your kind of rules for like good data visualization, especially for something like that?
Yeah, so I mean, a lot of this for me as bad as it sounds, it's like kind of dictated by marketing. And I think that marketing basically just comes down to communication. The thing is that you can make a tool that's really cool, but if it looks bad, especially in a YouTube video, people just won't watch it.
Yeah.
And I spent a lot of time creating the visuals of the original engine simulator with the specific idea that I wanted to put this in a video. And I even I did test screen captures to make sure that it looked good when it was screen recorded. And there was a whole process to this. Ultimately, you want to convey as in a video form anyway, you want to convey as much information as possible with the least uh, noise, I guess. You want to compress as much information into a um, understandable format that most people will be able to understand when they see it. So, if I just made an engine simulation and there's no engine on the screen, this is not going to be understandable to most people. They're not going to understand that there is an engine. Even if everything is the same, it sounds the same, it runs the same, there are gauges. It just doesn't mean the same thing if there isn't an engine on the screen. So, yeah, usually when I make my visualizations, it's just there are certain key things that I want to communicate, and I try to focus on communicating those in a way that as many people as humanly possible will be able to understand when you're looking at it. If I want to show, I think in one of my videos, I made a trumpet simulation or something, and I wanted to show the pressure waves that happen inside of an instrument that resonate in order to, or you get what I mean, the way that the standing waves form in the instrument. And there are different ways of doing that, but ultimately I settled on making it colorful and making it so that the tube actually grows and shrinks in real time. If it didn't move in real time, I don't think people would have cared as much. Or if you look at most fluid visualizations for fluid simulations, it's very useful from an engineering perspective. I mean, they have I forget what it's called exactly, but it has the lines showing velocity. I'm sure it has a technical name, but I'm not aware of what that is. That's very good and everything, but it's not necessarily that useful for visualization in video form. So yeah, there's a lot of I think that's where my work tends to get into more of the game design or marketing aspect of it. And yeah, I just I try to keep it as simple as possible and as visually appealing as possible. I know it's very subjective. I don't even know how to really explain that, but yeah, that's usually what I go for.
So speaking of your trumpet video, so I mean, a lot of my friends, their job is writing physical simulations, especially a lot of my old physics friends. One who's in astrophysics, he was simulating atmospheric dust, and he was also simulating magnetohydrodynamics of the sun, right? And a big thing in science is, one, you have to prove that it obeys some observational data, right? If you have that option. And two, there's some fundamental principles, does it conserve energy or something, that are generally accepted as necessary. For
Yeah.
you, when you're working on something that's aesthetic, there's still some need for ground truth. So one thing I love about your trumpet video is you pick up a trumpet, and you don't even no, play a trumpet, right? You're just well, let's see if we're on the right track here. What sort of ground truth have you done, if any, or has it mostly just been, aesthetic?
Um, as in rules for designing the aesthetics, specifically related to the aesthetics, not necessarily to the output of the simulation.
How do you ground it in the real world? What for you, how important is that, and how do you do it?
Right. And this is just for the visualizations or the simulation
No,
itself.
actually, I'm more talking about the sound.
Oh,
How
okay.
you doing to verify, to yourself that the sound's on the right track.
Yeah. So, I mean, a lot of I think the easiest way to check is energy conservation is probably the first check that I would do anytime that I'm doing a simulation of any kind. Because if you're not conserving energy, something's not right. I mean, that's just the instantaneous red flag there. So there are some theoretical checks that I do like that. in terms of grounding it to real life, I think it's a little bit easier for engines because like I built an engine in real life, I tested it, and I know all of like the power figures and what the general effect of installing certain things in engines is. And that was kind of how I calibrated the original engine simulator. I basically looked at like for example, your the volumetric efficiency with respect to the engine speed. This is a very it's not predictable exactly, but it follows a curve that is pretty common among a lot of engines. And if you're simulating it and it doesn't follow that curve, then probably something is wrong. So yeah, there's quite a lot of information available for engines, also in the research literature as well, which I use to kind of cross-check the output of the simulation. And ultimately, because I'm trying to make something that appeals to people that are interested in engines, the most important thing was when I make an engine, when I replicate a real world engine in the simulator and I run the engine on a dynamometer, does it match the results in real life? So that was really like and that's obviously a test of like the entire system as a whole. It doesn't really test any one thing in particular. And yeah, that was kind of like the most important sanity check that I did. And it worked out to be like not that inaccurate. I mean, for a tool that makes audio, the fact that it gave pretty accurate horsepower numbers for a lot of different engines that I tried was kind of crazy. And that was actually I think that was one of the main catalysts for the success, the initial success of that application is that it wasn't just people interested in video games that liked the program. It was also people that worked with engines in real life because they tried the program and they could see for themselves that the numbers actually matched what they saw in real life, and they ended up seeing maybe there's some utility in this pertaining to my actual job. So yeah, that was probably the main thing in terms of engines that I used.
Let's talk a little bit about like real-time simulation and latency. So like in a lot of our lectures, like we'll often show this picture that I've been showing for a couple of years, which is just like the full cycle latency path for what we do. So we have like real, bots will talk to you on the phone. And so, audio will hit someone's ear. They'll think about it. They'll produce speech. That'll go through the ear, it'll go through a microphone, it'll go through an ADC. It needs to go to speech recognition. It needs to go through a dialogue policy and language model. And then we have to generate a response and synthesize the audio, then replay it. And we show this whole cycle of all these things that are consuming latency budget. And so everything we do, because it has to be real time, is super latency constrained. And, I know that Natalie was, for instance, working on trying to get the latency down last year, and Phoebe too, actually. And you guys were, looking at anything that could shave, 100 milliseconds off of it, in terms of the full cycle, or for like individual models, anything that can shave, a fraction of a second decoding a language model token or whatever. And so we're like acutely aware of just real-time audio, how much more constrained you are and how many classic approaches don't apply anymore. So for instance, like a lot of state-of-the-art speech recognition is great, but it's nowhere near real time. It couldn't be used for a spoken dialogue system. For you, were there a lot of just approaches, I assume in the literature, that were all offline approaches where you just kind of had to one by one be like, this is not going to work for me? Or was it easy to kind of figure out, what you could adapt to a real-time application?
I think this was one of the advantages of starting with older literature is that like if you go back to the cutting edge of 1980, these would have been definitely offline simulations at the time, but they're not bad. I mean, they used them and they were effective then. Uh, so, I mean, it doesn't really take that much to get them to run in real time. I mean, it's not easy, but you can definitely get them to run in real time on a modern CPU. So there wasn't really much that I had to do in terms of cutting out stuff. I mean, there are like, obviously a 3D CFD that's not workable in real time for sure. I mean, not in the way that's used in like modern, let's say like an exhaust system analysis with like a 3D simulation. That's probably not going to work in real time. I think that one of the main difficulties was that this is not a simulation that like the real-time factor is very high. So what tends to happen is that your desktop is a really chaotic place. And if you're running something that's like this takes, this is like zero point 0.1 of your real-time factor, that's not really going to be a problem in terms of having defect-free audio. But the thing is, if you're running at like 90% of what the CPU can do in terms of just straight line speed, you end up with this problem of someone opens a program and then their audio is messed up and then they complain to me that they're, having audio issues and stuff. So, yeah, like definitely initially getting the program to run in real time was a challenge. After that, there isn't really a lot of latency introduced. Most of the latency is to just protect against just the random fluctuations in the user's PC to prevent like weird audio artifacts from happening. Um, but yeah, a lot of the techniques that I used are already pretty optimized for primitive hardware, and they run pretty well if you like write it in the right way and write it at a low enough level. So yeah, not too many challenges there, I would say.
Got it. It's really funny you talk about looking at papers from the 1980s that were clearly offline now, but now you can do them real time.
Yeah.
So in the previous lecture, we talked to John Chowning, who's 90, who was the inventor of FM synthesis. And in 1963, he invented this as an offline technique. Like computer audio was brand new.
Yeah.
And offline was just introducing a vibrato, and it got to the point where it was fast enough that it was in the audio band. And, fast forward like 10, 15 years later, Yamaha has licensed this, from Stanford where his patent was, and he flies out to Japan where they're building the DX7, like the first commercial, FM synthesizer, and he was just blown away to see it real time. Uh,
Mhm.
and something that for him, it started as you had to render just essentially multiplying, signs together.
Yeah.
So that's really funny that it's just like, oh, you just go back far enough, and their cutting edge is now real time.
Yeah.
Uh, So one question I had is like, what are like ambitions like that you have, like simulations you'd love to do, or if you have infinite time, or as you get to it, that you would love to see, or like that you've thought about.
That's a good question. I mean, engine simulation was always like the one that I had in my mind that I thought would be really cool. I never really thought about like what I wanted to do beyond that. I mean, I recently released Steam Engine Simulator, or at least like a major patch to Steam Engine Simulator, which is a similar idea. I mean, it's a physically simulated Steam engine, and it also generates audio in real time. And like, I tried to introduce some gameplay elements into it, which I actually think was more challenging than the simulation aspect itself. I kind of like the idea of like really large scale simulations or economic simulations and things like that. I might look into it at some point. I did a little bit of stuff like that when I was working in the investment banking area. That was mainly around like, Monte Carlo simulations and stuff like that. But yeah, I don't know. I haven't thought about that too much. I also did like a little bit of ray tracing on my channel, like but that's like a different kind of simulation, I guess. So, but yeah, right now it's going to be engine simulations for probably the next few years. I haven't thought that far ahead in the future yet.
We're gonna keep on chugging.
Yeah.
Let's talk a little bit about partial differential equations. They're really hard. Um,
Yeah.
and especially coupled systems of them, which fluids are an example of.
hmm
What have you learned about PDEs in this like journey where you're just, quietly walked into a very scary world?
Yeah, I mean, I'm not going to pretend like I'm an expert in this field at all because I definitely am not. It's very much like I'm just figuring it out as I go and trying to understand it to the best of my ability. I think that generally speaking, I think better in code than I do in terms of the math or explaining it in English. Um, but I like to see it's I don't know, I find it really satisfying to watch them work most of the time. And it is interesting that a lot of it seems very counterintuitive, I guess. Like for example, like the method of characteristics, which is something that used to be used a lot more frequently in fluid simulations. I don't like it's really hard to get an intuitive grasp of how that works, especially when they start like going into the math behind it. And yeah, like I don't at this point, I wouldn't say that if you gave me like a piece of paper, I would be able to solve any of these equations, even like numerically by hand. I could probably implement an algorithm to do it, just if I were to, if I had my actual code to copy. But yeah, it's just, I don't know. It's been really interesting. I can't really claim to fully understand it though. Like I probably couldn't explain it to you.
I mean, to be fair, completely working out just some of the fundamental principles of the Navier-Stokes equation is a millennium problem, along with all the other
Yeah,
forms of
yeah,
math.
yeah.
So I don't think anyone's quite cracked the code, and so I don't think it's just you. So I know. I mean, when I reached out to you, I know you were like a little hesitant. You're like, well, I don't consider myself like a sound modeling expert. I mean, one, obviously, like my dad, his advisor when he was in residency, like told him like you're not an expert in things until you tell people you're an expert in things. You're
Yeah.
definitely an expert in things, I'm telling you. But one thing that maybe I'm not sure how familiar you are with this, because it probably, I don't know how much you've dug down the rabbit hole of what other people are doing in like an instrument like sound generation. But like so like the first half of our course, we're talking about the kind of like musical instruments mostly as an example of sound generation, and then we're moving into speech.
Yeah.
Generally in state of the art musical instruments that people would use, to generate like a score for a TV show or something, if they're not recording a session musician, I think the two most common techniques are just using a sampled instrument where there's like gigabytes of data of people playing a real instrument under different conditions. And then there are physical simulations where they are doing essentially what you're doing, but oftentimes like choosing problems that really are amenable to physical simulations, like vibrating strings or drum heads.
Yeah.
Um, but increasingly in speech, and probably more and more eventually in other areas of sound synthesis, the most direct approach, if you want to, emulate these very complicated simulations, is to use neural methods, use like neural networks. That's what we do for speech generation. Is we actually have a neural network generating either a spectrogram, which we then turn into samples, or it's directly generating samples. Have you ever like thought about like learning more about like machine learning and trying to apply it to maybe fill in the gap between your simulation and a real engine, or have you ever have you like learned anything about like machine learning?
Yeah, it's been a common like suggestion in my comments section where people think that you could take
I'm glad I've been elevated to YouTube.
Yeah, well I mean you're maybe a little bit above a armchair physicist in my comments section, which there are a lot of them. Um but yeah, this it's an interesting idea. I don't know that much about machine learning myself. I did apply actually a very simplified machine learning type technique. This was so long ago that it's not like new in my mind, so I can't like explain it that clearly. But essentially, what it is it's like a predictive model. So and I use this on Steam Engine Simulator. So essentially, you have your stream of audio data that's coming out, and you have a predictive model that basically just learns from I don't know, the previous like 200 samples or so. I don't remember, a few hundred samples. And because it is kind of common that you'll have a situation where like you'll have a little bit of lag or something like that, and then you miss the next window for generating samples, it will just generate a few samples to fill in that gap. And then so basically you go from just zeros, which doesn't sound very good, and just sounds like popping and clicking. So you go from that to it sounds like a bit of a bit rate reduction, like nothing that most people are going to have too much of an issue with. Most people don't even notice it. So yeah, that's probably the furthest that I've gotten down the AI rabbit hole. Like it's a little bit of like linear like nothing crazy, like not like a neural net or anything like that. I guess you could consider it to be like a very primitive neural net, I guess, in the sense that
I get that a lot
the yeah, but nothing, yeah, nothing crazy.
Yeah, there's like two common ways that I think people will often use neural networks for things like this. One, there's something called like physics aware neural networks where like the fundamental physics, and then you have some ground truth data of the actual physical system. And instead of trying to predict everything with a neural network, you just try to predict the gap,
Yeah.
the perturbation. So like an example that I've always really liked is you can just try to have a neural network predict uh the dynamics of a drone, but then it has to like learn about lift and has to learn about Newtonian dynamics. But and it tends to perform pretty poorly at if this is like to use a neural network for a flight controller. But instead, what
Hmm.
you can do is give it the predictions from like Newtonian dynamics and the lift equation, and then just try to predict the delta. And that's really good for like things that are really nonlinear, like ground effect when it's close to the ground. And there's all, if you like look up physics aware neural networks, that's a big area. And for sound, it would probably work great. Because you could obviously just have it try to predict, from your starting point. The other thing that people often use it for is distillation, which is, you have the ability to, given like, your engine parameters, generate a lot of audio. You can then use that to generate all the training data you want to try to, just build a model for your own model. And that could be, that's mostly interesting if you want something that's less computationally intensive, but still produces, similar results as distillation. So those are both fun ones to look up.
Yeah, there was another like suggestion that I've gotten a few times is to basically take the output of the simulation and then use that as training data.
Yeah.
Because it'd obviously be like pretty difficult to get that training data in real life, but I mean the simulation can just run constantly and just generate whatever you want. Um, it would also be interesting, like now that you mention it, so the way that most physics engines work, or at least the way that the physical simulation that I use works, it can benefit a lot if you pass in a rough estimate of what the answer is actually supposed to be. And this is how a lot of them work. Like you basically take the output from the previous frame and you feed that in as kind of like a hint. I guess the best way to think about it would be like having a better starting point if you're doing there's I forget what the name of it is. It's like basically if you pass in a good starting point to like gradient descent or something like that, it ends up converging to the solution faster. So that could potentially be interesting if you had like a physical simulation with a bunch of constraints and you have almost like, because I can imagine myself, if I'm watching it, I can probably make some rudimentary predictions about where the best values probably will lie. And then you can maybe feed that in, maybe improve the calculations that way. I'm not sure, but yeah, could be interesting to try at some point. Actually, I just thought of one question that I do have. I get this comment a lot. Uh, People ask, is it possible to take, because they see in my videos like, oh, there are these tubes and they're like, making sounds. And their question is, can you use that to simulate basically like a human vocal tract? Now, I've seen various ways of doing this that don't exactly use like a CFD, but it's kind of like physically modeling those or that structure. I'm just curious, like, is that actually on the horizon for speech synthesis, or is it just more efficient to use, like, I mean, AI can already generate voices pretty decently. Is there even any room for that kind of simulation?
Yeah, so I think I have a pretty good answer on that, but yeah, Phoebe and Natalie jump in. So one, they've been doing physical simulations like that for many decades. I mean, they've been trying for 50, 60 years to build good physical models of the larynx and how it's manipulated by the transfer function of the mouth and teeth and everything. And there's even been physical simulations that have been built, which I think we'll probably show a video of in our class. And they can be pretty good at generating like formants and like vowel sounds and voiced sounds, where it really starts to break down. Even really modern attempts to do this, just completely from physical modeling, is as opposed to something like an engine sound, it really gets into the uncanny valley, where we have a
Right.
really high sensitivity to fidelity when it comes to speech synthesis. So even like earlier other methods of speech synthesis that were actually like pretty intelligent, that use like triphones and these like parametric methods that were like very sophisticated, they always sounded like very, off to us.
Yeah.
And even now with neural methods, we still struggle with what's called prosody, with how it sounds relative to how someone would emphasize a word or exactly how they would do it. Neural networks are really good about learning these little subtle details that help with the uncanny valley. And there's also just the data itself. When you're modeling from real microphone data, it's not going to just reproduce the person's voice, but the transfer function of the room, the transfer function of the microphone, puffs of air going into the microphone, and a lot of these subtle details that aren't like you're not maybe completely conscious of help sell that it's real, because it's not just that it's real, that you've really modeled with the neural network the larynx really well, or dental frictives really well. It's that it's also modeling sound of a person talking conversationally. So that includes things like intonation and how they break up words, and then also all these physical effects. And so a lot of these, just like the ground effect on the drone, there's all these weird nonlinear things that you would just never have the time or even thought to put into your simulation. Whereas with machine learning, it makes its way in, which is like one reason why physics-aware neural networks might be interesting for you, because you can generate an engine sound. You can probably very easily put it, add reverb and make it sound like your engine's in a giant, garage. But if you
Yeah.
want to actually, cover these like last couple little effects, like maybe the way that a piston rings or something, I don't know, like you might actually be able to capture that little bit of extra fidelity. The thing is, it might not be appreciated with an engine or an inanimate system in the same way it is with basically voices, hands, and faces, right? People are just super attuned to it. And so that stuff is like super uncanny valley, risk. And so that fidelity bar is just like incredibly high. And that's actually one of the things that we do that's different than other folks and have done for years, is we mostly record conversational speech. And we also record it on a microphone that's realistic for someone talking on the phone. And even that stuff makes a big difference. I don't know. I mean, Phoebe, there's other stuff too, right?
Yeah, the other main thing I'd add to that is just sequential dependence, like the way you say a specific word at different parts of a sentence, dependent on what words have come before it, words are coming after it, is extremely hard to physically model without an insane amount of modeling it differently for like a million different combinations of sentences.
Yeah.
And that kind of sequential dependence and exactly. And that's something else that neural nets are just kind of better at modeling sequential dependence based on data. And also you don't have to think specifically about why you change how you're intoning something, which
Right.
humans are very good at describing why they say things differently either. So having something that can just learn that from the data without us, it just sounds more natural.
Right. Makes sense. Yeah, I mean, now that you mention it, it makes sense that like certain tiny details would be more appropriate, or would probably be better handled by a neural network as opposed to like a physical simulation, because it usually is those areas where approximations have been inserted, I think is where a lot of the uncanny valleyness can arise. So it'd be interesting because I noticed also in like fluid simulations, like the flux limiters and stuff like that I was talking about earlier, it really seems like when they were designed, they are like an incredibly primitive way of processing the data in a way that a scientist reviewing the data or like a human observing the data would massage the data so that it continues to make sense. So it would be interesting if you had like an AI overseer that could manage that and still retain a lot of the detail that you don't want to miss in the simulation. Because like if you just smooth it out completely in the hopes of keeping it numerically stable, that's not good because then your audio doesn't sound good anymore. But if you had a way of preserving that detail, that could potentially also be interesting. But I don't know. I don't know. I don't know too much about the AI stuff, to be honest. But it is something that would be interesting to look into at some point.
Well, I mean, I know you love computers, so you'll love it.
Yeah.
We're really big on computers here too. So,
You know, as I said in my email, I really don't like perceive myself as being an expert in much of anything. I really just like to think of myself as a game developer and I guess audio guy. Somehow I like walked into this. Um, and yeah, like I'm more of like, what would you call it? A bit of a jack of all trades as opposed to like an expert in any particular thing. So like sometimes I do game development, sometimes I do graphics, sometimes I just do like a bunch of whatever I think is interesting and will, I guess, make people happy, or make people have fun while using their computers. That's really what I'm focused on most of the time. But I really appreciate the opportunity. Hopefully, someone will get something out of what I said. And yeah, that's pretty much all I have to say.
no, it's really our honor. I've been a fan of your channel for years. So thank you so much for your work. Continue to do it. Huge honor to meet you. Fan forever. And have a good evening.
All right. Well, thank you. And you guys have a good evening as well.
All right, thanks, Ange.